In this session, we're going to go deeper in looking at how we can understand associations to help us make decisions. And this is a very common everyday language, often touches on these kind of technical topics related to correlation. And that's what we're going to get to understand today in a bit more complete way. We're going to looking at how associations differ between different variables in terms of strength and direction. We're going to look at measures of variation between variables and learn a little bit about covariance and correlation. We'll be able to interpret those in terms of tables and also scatter plots so we can understand correlation. And we'll also look at how this is useful to see outliers and how outliers or unusual observations impact correlation. Correlations, they're not explanations, and besides, they can be as spurious as the high correlation in Finland between foxes killed and divorces. Now, it doesn't take a statistician to find some humor only in this statement. We don't really know what the speaker is saying here. Does this mean that there are fewer divorces, for example, or more divorces depending on how many foxes are hunted? It's really unclear if you actually start to think about it what the statement is saying, and that's the point, is that correlations are relationships between things, but it doesn't necessarily tell you whether one thing is causing the other. Perhaps, there are more divorces for any number of different reasons why. And there could also be another reason that's related to all of these things, and correlation isn't going to be telling us that. So it's those kinds of takeaways that we have to be mindful of as we're thinking about correlations with other kinds of data in our businesses. So associations between variables. We've been looking at descriptive statistics to understand how to summarize the data one variable at a time. But we see that there's increasing value of looking at relationships between more than one variable, so two variables or more. And these are helpful ways of graphically explaining or looking at those patterns so that we can have a more rich, a deeper interpretation of the relationships. And for that, we'll be using things like scatter diagrams, and trend lines that are super useful to see relationships, at least between two variables, or you can do patterns or sets of these things to look at more than one variable. These are techniques that are most appropriate and easy to use for quantitative variables. So those are going to be variables that have a range, such as interval data or ratio data. That's going to be the most useful. There are some techniques that allow you to deal with other kinds of data through transformations and apply these techniques, but the most traditional are going to be using quantitative data. We're going to be using one data represented on the x-axis, which will be the horizontal axis, and the other on the y-axis or the vertical axis when we actually do these plots. And we can actually look at a trend line, which will show the approximate relationship, the approximate linear relationship between the two variables to see what the patterns actually suggest. So this is what we're going to be illustrating. So here we have two relationships. One is a positive relationship here, looking at some kind of observation or data across the x-axis. This could be something like social well-being and maybe grades that are earned. You would expect that as a person has a greater level of social well-being, maybe they perform better in school or some kind of performance. And then a negative relationship here, we have the situation where some kind of pattern or something, maybe this could be the relationship between anxiety and grades here. And so maybe you would interpret that as anxiety is increasing, you would expect a negative relationship that grades would be decreasing. The point is that these patterns are very useful, and whether it's a positive or a negative relationship for correlation, they both give us very helpful information. This is what we're going to be looking at that. So to get further with this, we need to look at things in terms of measures of the strength of these relationships. And to understand those things, we have to look at things like covariance and the correlation coefficient. And so we're going to be looking at those measures. Covariance is simply the measure of the linear relationship between those two variables. Much like the variance that we saw when we looked at one variable, the covariance is going to be sort of equivalent to that. And the correlation coefficient, much like the standard deviation had a very simple interpretation, the correlation coefficient is closer to that. The Pearson correlation coefficient will have a range that's interpreted between plus and minus 1, which is a way of understanding the values and the strength of the relationship, that is how close it is to an overall pattern, almost an average of the trend line between the two variables. So this is just a tie back to some of the concepts that we've already talked about. We'll be just looking at them in new ways. We, of course, have the formulas here, and whether you're looking at a textbook or other sources, the formulas are very commonly represented. You might find a few differences in the notation. But again, in this class, being an applied statistics class, it's more important for us to understand how to interpret the data once it's actually computed using some kind of a tool or technique, at least a spreadsheet or some kind of statistical package. So here we can represent this, I think, in this illustration. We might have two measures. Maybe we have a measure of general well-being that we have maybe measured our students. You might recall in one of the prior examples, we had different measures of students in schools. So maybe we have a general well-being measure, and these are those values on there represented in the column X. And we also have measures of their anxiety, which we've measured here in column Y. What the correlation coefficient is doing is effectively taking the average first of the X values away from each value to get a deviation score. Same thing here with the Y values and get its deviation. And it's basically then just multiplying those things and adding it up so we can get a total. An we have that, we're able to utilize the standard deviation and the number of observations that we have to compute an overall score, which is used in the correlation coefficient. So once we do all that math, but again, the computer is helping us with that. So if you want to do it by hand, you can follow this example. We can see here we have a negative correlation of 0.9631. Well, what does that mean? Here I can interpret this correlation coefficient, which we know, and I'll show you how. It always ranges between +1 and -1. We have a very strong negative relationship here. And in this case, I can interpret it as general well-being increases, anxiety decreases. And we're pretty confident about this because of the really strong correlation, at least in this sample data set. So how do we make that interpretation, and what does that picture look like? Those are really the best questions that you can have as you're looking at these kinds of data. Here I have represented a number of first positive relationships. So in the prior example, we're looking at a negative relationship. I'll show you what that looks like in just a moment. But here we have a number of positive correlations of various strength. So the Pearson correlation coefficient always ranges between -1 and +1, and correlations that are near 0 have practically no pattern or no relationship. So we have here in this example of a correlation of 0.1. You can see how the relationship between two variables, maybe this was the variable of well-being and anxiety. We didn't see this pattern a moment ago, but if the data that we had just observed between well-being and anxiety came out like this, I could basically make a determination that the two are pretty well not related to each other, that there is no strong pattern. There's no strong strength or direction that I can interpret between well-being and anxiety. Now, as I go up in strength, so now I have a positive correlation of 0.5, you can see that the data begin to sort of cluster around each other. And I increase the strength even more to 0.7, it almost starts to take the shape. And you can almost imagine now a line that would best describe or approximate all the values. And that line gets quite strong or clustering around all the points by the time that I get to a correlation of 0.9. And we had the opposite situation a moment ago with the strength of the relationship, though, was the same. Here I have a positive relationship. This would be probably the example more about general well-being increasing and grades increasing. For example, a simple example like that. So we can see that there's a really strong relationship here around 0.9 if that were the data. And that means that all of the observations are pretty well clustered closely as I go in any one direction, a 1 unit increase in, say, general well-being, I can almost guarantee I'll have the same unit increase on the other measure. And that's what's telling me that there's a strong relationship. And it's very well describing all of the data. Much better than a straight line over here, which really doesn't describe any of the data. You'd have a hard time drawing a straight line through any of these points and accurately defining all of them. That's really what correlation is helping us understand. Now let's look at the opposite situation around negative relationships. Does a negative correlation mean a bad thing? Well, no, it just means that the pattern of the relationship is in the opposite direction. So here I have represented a number of strengths of correlations, and you can see, again, as I have a correlation of minus 0.2 to minus 0.4 to minus 0.6, you can actually start to now see how a line might define those data pretty well. And here I have a correlation of minus 0.8. This is really now taking the shape of a line closely describing as best it can with minimal error if I were to draw it through all of those data points. And that's exactly what the correlation is telling us. Here I do have the situation, as I saw earlier, as general well-being is going up on the x-axis. Now I can see my anxiety is falling, for example, and now I have a strong negative correlation. In this example, it might be minus 0.8. I think the example we had earlier was something close to minus 0.6, 9.6. But both of these basically just telling me the strength and the direction of the relationship. It's not a bad thing. It's actually a very good interpretation. The stronger then I'm able to interpret that correlation coefficient. So here's another way of representing that. Correlation could be positive, and what I've been using these words of weak, I know from experience of looking at data like these and with charts that I've just shared with you, values that are plus or minus 0.2 are relatively weak. As you're getting up closer to that 1.0, that's the maximum range. In fact, I'm going to demonstrate this in a moment. If you're at plus or minus 1.0, every single observation in the data set are falling exactly on a straight line. That's very strong. And we have virtually no relationship in the center. So here's what some of those data would look like. If we have a perfect linear relationship between two measures, again, this might be, this could be general well-being, for example, and maybe GPA. Or scores in a class, every single observation would fall directly on an imaginary line that goes through the data. And we have the opposite going on over here. Again, maybe this is a negative relationship as general well-being is increasing, something like anxiety is clearly decreasing, and so you have all your observations falling along those straight lines. So the Pearson correlation is a way of helping us understand and interpret that very quickly. The value would approach 0 when there's a very weak relationship. Now, it is important to understand that there could be data that line up along observations like this. Like what is this sort of a pattern telling us? Well, as I can see here, as I look across the x-axis and I have a measure, maybe this is something like social well-being, every time I have an observation of well-being measured, which might be right here, on the y-axis, which might be anxiety, I don't gain any new information, no matter what level of social well-being I've actually measured. We can see this, every single observation has the same level of anxiety. This would be an example where there's no correlation because there's no information gain, there's no pattern to discern, regardless of the level of general well-being that I've measured, if this were the case. Now, we know that's not the case. We've already looked at the data, but this is just theoretical. Now, we also have the same situation here. This would also indicate no correlation because there's no information gain. I have the same value every single time on the x-axis, independent that the y-axis is changing. It's really equivalent. So I have no correlation represented in both of these. Now, this is also a helpful tip because sometimes when you try to correlate categorical data, for example, if males have some kind of observation of males and you're looking at the correlation of some measure, which could be, say, anxiety, that might be, this could be a pattern where the computer comes back and gives you a correlation of 0. That's because there's absolutely no variation in males, because we're using a categorical variable, which is males, to try to use correlation, maybe inappropriately, to look at a relationship. So the computer will come back and say, hey, look, correlation is just 0, because there's no variability on the element of male. It would be a different kind of a technique, but if you introduce females in there, the computer might actually give you some observation, but maybe there is a difference between males and females and on that. But you need some variation on both measures. So going forward, what's most likely, though, is you're going to ask for, appropriately, correlations between a number of measures. So here I've returned again to the general well-being measure that we had before. And we also have IQ and some other measures, depression, anxiety here. Now, what this table is telling me, it has a very interesting pattern here on the axis that's along the diagonal. So what this is saying to me is, naturally, if you think about this, if I had a correlation of the IQ measure to itself, every time I had an observation of an increase in IQ of whatever the measure was, I would observe that the exact same unit increase was happening on the opposite axis. In other words, all those points were perfectly lined up. And that's exactly what the correlation table is telling us. In fact, it's a mirror image of each other, because the correlation table is showing us two variables that are related to each other. And you'll see that pattern. If I ask for the relationship between depression and anxiety, I can see the same values, depression and IQ. I can see the same values here and here, whether it's above or below the axis. They're going to be the same number, because it's a mirror image. The computer is just showing you whether you want to think about one variable on the x-axis, which I often do. It helps me with interpretation. And y-axis is which one you start with. But the measure is going to be the same. And that's why you see this. And it's important to look at that at the table. And sometimes some people will, in fact, represent only half of the correlation table for that reason, because the information is totally redundant with each other. So you may only see half of a table, which will be the bottom half or the top half, depending on what it is that's being measured and reported on. Now, let's go back just a little bit more to the interpretation of what this is telling with us. We were looking at the general well-being as an example. The general well-being is negatively correlated with depression, as we had talked about earlier, and we can see it here at negative 0.801. This is telling me that there's a relatively strong negative relationship. So as general well-being is increasing, my depression scores are decreasing. Now, I can also see I have a positive relationship here with total functioning, total social functioning. As general well-being is increasing, my general social functioning is increasing. So that's a way to interpret the correlation table. Very useful way of representing the data. Now, I want to look a little bit deeper at some of the plots of the correlation. I had a theoretical example, but here's some actual data between the general well-being and the depression scores. And we can see that there's a negative 0.80 negative correlation. And so clearly now, as general well-being is increasing, as those scores and those observations are going up, I can see that my general depression scores are going down. And so we have a trend line that best describes the relationship between all of those points. And at a Pearson correlation of negative 0.80, I can see that they're relatively closely clustered around that line. So there's a pretty strong relationship there. Here I have a relationship between general well-being and social functioning. So it's a positive relationship. I can see 0.33. So as general functioning, general well-being is going up, social functioning is also going up. But I can see from the dispersion of the data that the strength of that relationship is just not as strong as the prior example. And we were able to measure that, and I knew that because I've worked with the data a long time, and I know you will as well, that this relationship is just not as strong. Correlation of 0.33 is not as strong as a correlation of negative 0.80. Even though one is positive, one is negative, but the strength of the relationship is what we're trying to illustrate here. And the strength of this relationship is weaker than the prior example. Now, in an earlier session, we actually looked at a concept known as Simpson's paradox. Simpson's paradox can occur when we've aggregated data and rolled things up to an average, and it hides a relationship between two subgroups. And this is another helpful way with a scattergram of representing how that can happen. Here I have plotted the general well-being and social functioning of students at a school. And here I can see that there's a positive relationship, as we might expect. As general well-being increases, the social functioning of these students also increase. And then I might take that measure at a second school, and again, I find a positive relationship. As the general well-being increases, I also see social functioning increase, albeit this is at a lower level. You can see that, the social functioning now of the students in green is relatively lower, even though their general well-being is higher. We have a different pattern here. General well-being is relatively lower for the students in red. Their social functioning is higher. It's sort of a bizarre situation, but it's meant to sort of illustrate a point. Now you can see the positive relationship between these two subgroups. If I stopped my example there, everything would be perfectly fine. But what happens with Simpson's paradox is we might go further and try to describe the pattern overall as a linear relationship. And when the computer does that, it's going to try to connect all of the dots with a single line, a single linear line. And when it does that, you're going to have a situation in the computer that looks something like this. Now it's completely changed the relationship and our interpretation. Now I would interpret this, if the computer came back with a score, that as general well-being increases, social functioning is actually decreasing. You can see that right here. And this is exactly the way that the computer would treat this data. It's very unusual, but this is why it's so important to make sure that you look at the subgroups that you might be aggregating up to a wider, larger group, and make sure that those relationships are not dramatically different than what you would expect. Because here we have a paradox going on, and this is a linear regression way of demonstrating that. It's very unusual. Now, another important thing to look at scatter plots for are outliers. We had looked at this in a prior session, looking at different histogram methods of looking at outliers or unusual observations. And we can do the same thing here with scatter plots. When we look at IQ scores being plotted going from lower to higher, and anxiety test scores here, we can see the general pattern is a positive relationship. And I actually measured the correlation using the actual data in the data set, and I found that the positive relationship is 0.38, positive correlation. So there's a moderately strong positive relationship between IQ scores and anxiety. So as IQ scores are going up, actually I see anxiety test scores are actually going up. In this case, I may have said social well-being. Forgive me if I did that. There's a significant moderately correlation between IQ scores and anxiety. Now, the thing is, I already had it highlighted here. We have an observation that's an outlier. We have somebody in the data set that has 0 IQ score, which is not possible. So we know we have an outlier. In this case, it's not an outlier I want to pay more attention to. It's an error in the data, and I want to take it out. And when I do that, I have the new plot that's on this side of the slide. By taking that out, I now see that the relationship has changed. I have a significantly less, it's a very weak relationship now, very different interpretation that I had over here. Now I have a non-significant and a weak correlation between IQ scores and anxiety. We're going to come to the significance part, which is basically the p-value in a later session, but right now you can see that the relationship did change. And on this side, if I leave that observation in, I think that there's a moderately positive relationship. Over here, it's a very weak and a non-significant correlation. So it's very important to pay attention to outliers, and scatter plots are one way that we can see that. Here I have an example where we want to understand how a linear relationship is represented in the scatter plan, in the scatter plot. And sometimes we might see that measures are on different cycles. So let me roll this back. Here you might start to say that across the year, as the year goes on, maybe I start in January and I'm going to go to December, I can see that sales are decreasing. And so this tells me perhaps I have a product or service that as I go later in the year, people are using it less. Maybe it's something in the United States. Often we have snow blowers, for example. So snow blowers might be a very popular item. And then as maybe it gets later in the year, I can see that the snow blowers might be dying down. However, as the pattern continues across the year, with my snowblowers, that's not the end of the story. In the US, at least, as the months of the year get later, I can see my snowblower sales start to pick up again. So now what we have is a curved linear relationship. When we look at things like correlation, correlation is trying to draw a linear line, a straight line through all the points. So the computer is going to probably produce something like this, and the linear relationship is going to look flat. And that's an artifact from the method trying to draw a single linear line through all the points. And you can see here, you're going to miss a very important pattern. You actually have a curved linear relationship, and the computer is telling you, well, there's no linear relationship between these two variables, such as snow blowers being sold in the United States, but there is definitely a curved linear relationship. And if I were in the snow blower business, it would definitely tell me I need to pay attention, not so much in the summer months where it's warm here in the US, but in the winter months where it starts to cool down. I'm going to see the pattern change with sales decreasing and then increasing. That's going to be very important to my business. Now, another thing about correlation is the scale that we measure the relationship on is not affected. The correlation does not get changed. It is not affected by the scale by which we are measuring our variables. So here is an example where I have my customers' age in years going up, and the sales we can see here. So this is basically telling me as my customers get older, the number of sales that I'm getting from them are decreasing. I tend to be selling to younger. But if I replotted that and instead of had customers in age in years, maybe I had age in months, you can see that while the pattern looks a little bit different, the measures, that is the correlation coefficient, which is showing me the relationship between the two variables, are not going to change. So this is an important concept as you start to work with data and you look at things measured in different ways. Understand that the relationship is not going to be affected by that, whether I'm looking at something in months or in years or in metric versus some other measure. You're going to find the same pattern because it's talking about the strength of the relationship, and that's not so important on the way that you're actually measuring things. So here we have the same kind of negative relationship between these two measures. When we started the session out, we talked about the relationship between foxes and divorces. I think it was in Finland. And this is really important to understand in correlation, that it doesn't mean that things are causally related. So does knowing the level of one thing help you interpret or know something else? So education level and income, for example, or past sales and future sales. These are important common ways that we would look at correlation. But I'll take the example of education level and income earned. It could be that the more education you have, the higher your earnings. But it could also be that the more earnings that you have or your family has, the more education you could obtain. You can see that the causation of one outcome is not completely explained by the other, and it could work in either direction. There was a funny example shared many years ago. A research team found that in the United States, ice cream causes drowning. That was the headline in the newspaper. But you have to reflect on that, because the reason why ice cream, at least in the US, is consumed in the summer months when it's warm outside, then people are typically in places where they're swimming. And so there, unfortunately, are more drowning deaths in the US in the warmer months, mostly because the weather is warm and people are doing things that would increase the risk of them drowning. It has just a spurious relationship that also, when the temperatures heat up, people are also eating more ice cream. But you can see how you have to understand what you're looking at. These are silly examples that sound very obvious, but most of the time when you're starting to work with data and you're unfamiliar with the measures, you could start to detect patterns and start to think about things from a causal relationship. And you need to really take pause there and make sure that you're interpreting a relationship in multiple ways before you jump to any kind of a causal relationship. It's better to talk about things as being related and use experimental designs to see how things are causally connected. And we'll get to that later in the class. One last point. We've been looking at Pearson correlation coefficients, and those are appropriate when the data are continuous kinds of numerical data that you can measure in quantitative fashion. If your data are other types, there are other versions of correlation that are more appropriate. And you might see variables like these kinds of measures for chi-square or Kramner's V or phi being used. So knowing the type of data that you have, the statistical package can offer you different kinds of measures. And rather than calculating these things by hand, we'll illustrate those where appropriate when we're working with the data so that you can select the right one. The good thing is that the interpretation is somewhat similar. They're all going to be telling you about the strength of relationship between things, and that's a good thing for helping us make sense of the data and having some interpretation of it. So the takeaway on today's session, what we've been looking at are how we use scatter diagrams and scatter plots. Very useful for us to look at relationships between the direction and strength between variables. We saw what it would look like and the effect on different outliers. We used the covariance and the correlation to help us interpret the strength of the relationship between the variables. It's basically a measure of dispersion. And when we had low levels of covariance, we knew that two variables were really tightly related. So as well-being was going up, we saw anxiety going down, for example. And outliers may change the interpretation and the association between those variables. We have to be mindful of that and then decide how to appropriately use those, whether that's something we want to retain in the data set or maybe hold out because it's obscuring the relationship between the wider set of our data.